Welcome to Unit 3, the periodic table. This is the first part of your notes. So when you're taking these notes, you can go ahead and fill them out. Pause anytime you need to fill out the things that you need on your guided notes sheet or on your own note sheet. And make sure you go back and re-listen to anything that you missed that if you want to hear again. I will say a couple more things that are extra that you can definitely add to your notes as well. So talking about the periodic table, there are reasons that it's organized the way it is, not just because of the electron configuration, but what you'll notice is that there are certain properties that they have depending on where they are located on the periodic table. It does have to do with that valence shell and how many electrons they have in the outermost shell, but we can notice a lot of trends just by looking at the periodic table, and we can predict the properties of those elements, even if we don't know what they have based on where they are on the periodic table. But today, first, we're going to go through the history. Just know the people and their proposed findings in general, not the entire thing. Overall, you don't have to exactly understand everything, but just know the people and their proposed findings in general. First, we have de Bruynier's law of triads. His law is only true for a certain collection of elements, not all of them. You can see the examples on the slide where it does work. And we have certain elements in groups of 3 you can see here where we do have the law of triads where it works. What the law of triads states is that the middle element, so if you looked over here, we have 7, 23, 39. 23 would be our middle element. In the group of the triad, in the group of 3 elements, has an atomic weight that was the average of the other 2 members. So if I add 7 plus 39 and divide it by 2, I should get 23. If I do 40 plus 137 and divide it by 2, I'd get 88. You can see the example down here. And if I had 35 plus 127 and divided by 2, I should get 80. So when we're looking at the atomic weights, we can actually see that when you divide the outside 2, the middle one is going to be the average of those. Doesn't work for all of them, again, only works for certain ones, but de Bruyner noticed this in 1829. So a long time ago, he did notice this trend in the atomic weights. Next, we have the law of octaves. John Newland proposed the law of octaves, and what he said is pretty much when elements are arranged in increasing atomic mass, so again, going by their weights, when you put them in by increasing atomic mass, the first and the 8th elements will have similar behavior. So if we look at his example over here, these are ordered in increasing atomic mass all the way down. Hydrogen through oxygen, fluorine through sulfur, chlorine through iron. When he does that, you notice that your first and 8th elements, all my first ones and all my 8th ones, are going to have similar behavior, and behavior repeats in a periodic fashion. So not only do these first and 8th but if you notice the second and those through also as well have similar behaviors. That he based it on chemical properties and atomic weight. Different elements with similar chemical properties are usually separated by a multiple of 8 mass units, is what he noticed. For example, if you do look at it, hydrogen, fluorine, chlorine, bromine, and iodine, they're all on the same interval here, on the same line, same interval. They have similar properties, and we know that based on what our research of chlorine, fluorine, bromine, all those have now. But in that time period, in 1863, Newland did recognize this periodic properties, how the first and 8th have a repeating pattern in the periodic table. Little attention was paid to his work because he linked his finding to music, so they didn't really think that it was actually relevant or reliable information because it was linked to music. But we do know now that actually a lot of the periodic table does relate to, and chemistry does relate to music, and it's kind of cool. But back in that time, they paid little attention to the law of octaves because he related it to music, and they're like, okay, he's just crazy. Now in 1869, we have Mendeleev, Dmitry Ivanovich, I can't say his name very well, Mendeleev. But the key thing here is remember, Mendeleev is the father of the periodic table. That is a test question. He is a very important person. Pretty much is the one who came up with the main idea for our modern periodic table and the organization. You can see in the picture here on the left, that is what he called the periodic table. It has periods, which are your rows, and groups, which are your columns. Just like our modern day periodic table, it has both of those. It was arranged with increasing atomic weight and attention to chemical properties, which is the same as what we have with our modern periodic table. The difference is we don't go by increasing atomic weight, we go by increasing atomic number now. But back in Mendeleev's day, he did start with weight first before he realized before another realized that atomic number is really what they're increasing by. The key thing about Mendeleev as well is because he arranged it not only by the increasing atomic weights, but also by their properties, he noticed where there was gaps in the periodic table and left those gaps in there. He also then predicted the discovery of new elements that could fill those gaps and what they would be like. So he not only predicted what their atomic mass would probably be close to, he predicted the properties they would have based on what else they were in the same column or group as. The ones that he did predict were Eka aluminum, Eka boron, and Eka silicon. And then we know them now to be gallium, scandium, and germanium. Once they discovered germanium, that provided the best confirmation of his predictions for the time. Mendeleev pretty much did is just notice those chemical properties and started grouping them and developed a table to organize it. And doing that, you can see his quote down here. In doing that, we call him the father of the periodic table for pretty much making the first periodic table. In 1871, so just a little bit later, we have Lothar Meyer. He was a German chemist, and he independently published a nearly identical table to Mendelev's. He did pretty much almost the exact same realization. He worked with Robert Bunsen, who also worked directly with Mendeleev. Meyer and Mendeleev never directly worked together, but they worked with that common mutual friend. So that might be part of the thing that we might want to give Robert Bunsen some of the credit there, because maybe he kind of like bounced the ideas back and forth between the two. But what Meyer called his periodic table was the periodic chart of the atoms, and he arranged them according to atomic volume and weight. And then in 1906, later on, Mendeleev did come within one vote of receiving the Nobel Prize in Chemistry, later on after all of this stuff was done. Next we have in 1914, we have Moseley's periodic law. It starts with Rutherford's landmark Goldflow experiment, if you remember the very first unit, talking about him finding the nucleus and then eventually the proton in 1911 through his Goldflow experiment. Moseley was able to derive the relationship between X-ray frequency and the number of protons. So he was actually able to start discovering how many protons there were inside the nucleus of each of those elements, and we could use the atomic number of the element. So if we know the atomic number instead of the electrons we're looking for, we can predict the wavelength of the lines. So he pretty much just used the X-ray frequency, and remember we learned about frequency is how fast the heart beats. Wavelength is kind of how long and slow. Longer wavelengths are going to be, the space between the wave to wave is going to be longer. Less frequency, inversely related. He noticed that relationship between the atomic number and the wavelength. And instead of ordering the periodic table by the atomic masses, he switched it and he started organizing the periodic table by the atomic number, by how many protons they have. That gave the table much better organization and fixed the little bit of inconsistencies that they noticed with the atomic masses when they organized it that way. They noticed that sometimes they didn't quite have the same exact properties and that they'd do better if they flip-flopped them. And we know that there are some that their atomic weights do not go in order the same as their atomic numbers. So the atomic number was a much better organization, fixed the inconsistencies, and now the properties on everything on the table made more sense. So again, remember the atomic mass does not increase the same order as the atomic number for all elements. Just remember to look at iodine and tellurium to see an example of that. So Moseley's periodic law arranged the elements according to increasing atomic numbers and not atomic masses, and then it fixed those inconsistencies that were associated with Mendeleev's table. The modern periodic table is based on Moseley's periodic law, which is the increasing order of atomic numbers. At age 28, Moseley was killed in action during World War I. So actually his discoveries were before he was 28. So if you ever think that you're doing really well for yourself, you just remember that a lot of these people were very young when they discovered these crazy things. There was lots of intelligence back in those days. Our last major change came in 1940. We have Glenn Seaborg. He discovered the inner transition metals, our transuranium elements, atomic number 94 to 102. Our transuranium elements are created by nuclear bombardment. In the very last unit, we talk a little bit about nuclear chemistry and how we create those, but you pretty much force those elements to be combined together to make a new element. That's nuclear bombardment. This reconfigured the periodic table by placing the lanthanide and actinide series at the bottom of the table, all of your F block. In 1951, he was awarded the Nobel Prize in Chemistry, and element 106 was later named Seaborgium in his honor. That is a test question, so remember that. Remember which element's named after him or which one of these guys is the one that got the Nobel Prize. That's Seaborg. He's the only one of the ones that we talked about today that actually got the Nobel Prize in Chemistry for his discovery and development on the periodic table. And he does have the element named after him. He also predicted that there's a G block that will come underneath the F block, and it'll be between the S block and the F block, coming in at the 8th period. So the next line down, if we ever make more elements than oganesson, we're going to start coming into a 8th period, have an S block and then a G block, and then go back into another row for F block. Now we're going to talk about the different types, the metals, nonmetals, and metalloids on your periodic table. You can see in the bottom right picture down here, we have our metals, is what majority of your periodic table is. There's also a little bit of nonmetals and then a few metalloids. So fill in these properties of these metal or these different elements. You will want to know these very well. So first we have metals. Most elements are metals. 88 elements found to the left of the zigzag line. So if you look on this periodic table or yours, you can see there's a zigzag line. All of the metals are found to the left of the zigzag line. Their physical properties, they have luster, which is just how shiny they are. They're good conductors of heat and electricity, so heat and electricity pass through them easily. Your copper is a good conductor of electricity, that's a metal. You have high density, so really that just means, remember how they're dense, so you do mass divided by volume, so for their size, they're pretty heavy. They have a high melting point, so you have to get them really hot before they start melting. They're ductile, which means you can draw them out into thin wires and not really lose. They're not going to bend and break, they're not brittle. And then they're also malleable, which you can hammer them into thin sheets. So again, they're not brittle. They're pretty easy to develop and change and shape how you want to. The chemical properties of metals, they easily lose their electrons. They're often going to be cations or positive ions, and they corrode easily, which just means they break down, or like your iron will rust. They corrode easily. Then we have our nonmetals. They're on the right of the zigzag line plus hydrogen. So not all of them are to the right of the zigzag line because we do have hydrogen that's hanging out over here in the S block on the first, in group 1. Their characteristics are the opposite those of metals. So you can draw a line and say opposite, opposite, opposite for everything pretty much with nonmetals and metals. So physical properties of nonmetals, they're poor conductors of heat and electricity. They don't conduct heat and electricity very well. They're also not very shiny. They're usually dull. And they break easily, so they're not ductile or malleable. You can't make them into wires, can't pound them into sheets. They have a low density, so usually they're pretty light for their size comparatively. And they have a low melting point. It is easy to take them from a solid and melt them down into a liquid. The chemical properties of nonmetals, they tend to gain electrons. They form negative ions called anions. They're going to gain extra electrons and form those negative ions. Next we have metalloids. These are elements on both sides of the zigzag line, so they're touching that zigzag line. Aluminum is an exception. It's touching the zigzag line right here in the group 13, but it's actually just a metal. They have properties of both metals and nonmetals. Their physical properties, they tend to be solid. They can be shiny or they can be dull, it just depends. They have properties like metals in that they're ductile and malleable, and they conduct heat and electricity better than nonmetals, but not as well as metals. So they're kind of just the middle ground. Their chemical properties, it just depends on where they're located. They can form cations and anions. So metalloids are kind of just like the things we throw together that have properties of both that we're not really sure where they fit. But they are all found along that zigzag line. You can see the metalloids in the pictures here. Last thing you're going to want to do is you're going to want to label your periodic table with what the meanings are. On your periodic table, you should have a 1 at the top. That's your IUPAC number, which is just the official naming, chemistry naming association. The second number down is the European number, and the bottom number is the American number. So you have 1 on the top, it's the IUPAC. You have the Roman numeral 1A, which is your European, and then the bottom one is 1A with a normal American number. That's your American number, 1A. Notice as you go across, there's 1A, 1B. Different ones use different numerals or numbers to number those. Most of the time you'll go by the American or the IUPAC number to help you remember these things. One last thing to remember, group or family, those are the vertical columns, so up and down, those are all different groups or families as we talk it. As you fill out your periodic table, which you should do next by watching the video or looking at the examples, you're looking mostly at the families, the up and down vertical groups on the periodic table. Your periods are horizontal. They go long ways across your periodic table. That's a period. So you have 1, 2, 3, 4, 5, 6, 7 periods across, and you have 18 groups.